Question 9, and this is the information we've got. It gives us the delta H of neutralisation in the reaction of sulfuric acid and sodium hydroxide. Remember, that's the enthalpy change per mole of water formed in the neutralisation reaction. And these are the amounts of each substance added, but this time they may not be in exactly the right proportion, so one or other of them may be in excess, and our first job is to work that out. So for that we need an equation, which is what it asks for. So we have sulfuric acid plus sodium hydroxide will give us sodium sulfate plus water, and that needs balancing. You can see we need 2 sodium hydroxides to balance the sodium, and then if you balance the hydrogens and oxygens you discover that you get 2 waters as well. So that's your balanced equation, and the importance of balancing it is that it tells you it's a 2-to-1 reaction. So if we work out first of all the moles of sulfuric acid, so the moles is concentration times volume in dm cubed, which is 1.00 times 0.03. Okay, 30 cm cubed divided by 1000 is 0.03. dm cubed is 0.03 moles. So what the equation tells us is that if all of those 0.03 moles are going to react, we need twice as much sodium hydroxide. So in other words, we'll need 0.06 moles for all of that to react. So if all of this is going to react, we need 2 times 0.03, which is 0.06 moles of NaOH. Okay, and that comes from the equation. So then we compare that, which is what we would need, with what we've actually got, and that will let us figure out which one is in excess. So for the sodium hydroxide, we get the moles added is again concentration times volume in dm cubed, which is 1.50 times 0.025 dm cubed, again dividing the 25 by 1000, and if we work that out, that comes to 0.0375 moles. But we worked out that we needed 0.06. Okay, so 0.0375 is less than 0.06 moles, which means that there's not enough to react with all the sulfuric acid, or to put that another way, the sulfuric acid is in excess. Okay, so that's quite an important little calculation. First of all, you can see we needed a balanced equation. Balancing was crucial there because we had to know that it was a 2-to-1 reaction in order to work this out. And then we can work out the moles of each substance added very easily, just from concentration times volume. But the bit you have to explain carefully is how you then work out the excess. So I just picked one of them. I could have started with the sodium hydroxide and done it the other way round. So it didn't matter which one I started with, I just chose to start with that one. And said, right, moles of that one is 0.03. The equation says I will need twice as much sodium hydroxide, so 0.06 moles. And the question is, have I got that much? If I got more than that, sodium hydroxide would be in excess. If I got less than that, the sulfuric acid would be in excess. And you can see it worked out we had less, so the sulfuric acid was in excess. Okay, so this is what we now know. That's the moles of sulfuric acid we added, that's the moles of sodium hydroxide we added, and we decided this was in excess. Now what that means is that not all of that sulfuric acid reacts. So we can't calculate the moles of water formed from that, because some of it reacts and some of it doesn't. So we then say, right, we're going to ignore that because that's too complicated. But if we focus on this, that's easy, because this isn't in excess, therefore all of it reacts. And so we can use that for the calculation. So we then look at the balancing numbers again. 2 moles of sodium hydroxide go to 2 moles of water. In other words, however many moles of sodium hydroxide we have, we'll get the same number of moles of water. So we can just write down that moles of water formed is equal to moles of sodium hydroxide reacted, which is 0.0375. And that's what we need to do the next bit of the calculation. So in part 3, it wants us to calculate the temperature rise that we expect to get in this reaction. So remember that the relationship that's going to come from is Q equals mc delta T. But again, we've got to rearrange that to get what delta T is equal to. So we take the mc and slide it across to that side. Q over mc is equal to delta T. So that's what we've got to calculate. So now we have to set about finding Q and M so that we can calculate delta T. So Q comes from the fact that we know delta H of neutralization. So that's minus 57.9 kilojoules per mole. What that means is that each mole of water formed releases 57.9 kilojoules. Okay, so that's the translation of what kilojoules per mole means. It means each mole releases 57.9 kilojoules. And when you think about it that way, it's fairly obvious that the total heat released is therefore 57.9 times the moles of water. Right, because you can see common sense tells you if each mole releases 57.9, if you had 2 moles, it would release 2 lots of 57.9. But we haven't got 2, we've got 0.0375. Okay, so that equals 57.9 times 0.0375, which works out as 2.171 kilojoules. But now we have to do this kilojoules to joules thing in reverse, because C is going to be in joules per Kelvin per mole. So Q has got to be in joules per mole so that the units of energy, the joules, are compatible. So you've always got to check that. So that's equal to times 1,000 gives us 2,171 joules. Okay, equals Q. Right, so we've got that number. Then what about M? Well, that just comes from the total volume. Okay, so we've got 30 cm cubed plus 25 cm cubed. So we've got the total volume is 30.0 plus 25.0, which is 55.0 cm cubed. And again, we do the density equals 1 gram per cm cubed approximation, and say therefore the mass M is equal to 55.0 grams. So finally then we can feed those numbers into this expression that we had for delta T. So Q was 2,171 joules, we'd worked out. M is 55.0 grams, and C, as always, is 4.18 joules per Kelvin per gram. So you can see the units are all compatible, joules and joules, grams and grams, and so on. So if you crunch those numbers, you come up with 9.4 is the answer. So 9.4 Kelvin, or 9.4 degrees C, is the temperature rise. In question 10, it gives us the delta H of combustion, and it gives us the volume of water and hence the mass of water that needs to be heated, and it gives us delta T, and we have to work out how much carbon has to be burnt in order to achieve that temperature rise. So the first thing is that we can work out Q, okay, because Q is mc delta T, and M is the mass of the water that's being heated, so that's 500 times 4.18 is the specific heat capacity, and delta T, 100 minus 20, is 80.0. So if we calculate that, that comes to 16720 joules, and as usual we'll convert that into kilojoules. Sorry, I missed out a zero there. 167,200 joules, which is 167.2 kilojoules. Right, so that's the amount of heat that's needed to produce that big a temperature rise in that mass of water. And now we need to work out how many moles of carbon we need. So again, we can translate that number and say each mole of carbon releases 393 kilojoules. We need 167.2 kilojoules. So all we've got to do is work out what fraction that is of 393, and that will tell us what fraction of a mole we need. So that means that the moles of carbon needed is the total amount we need divided by the amount per mole. So 167.2 divided by 393, which comes to 0.425 moles. And then we just have to turn that into mass in the normal way. So mass is equal to moles times AR, because it's a giant molecular structure, remember, so no molecules there, so it's 0.425 times 12, which comes to 5.10 grams.